In this video, I'm going to take you through the drawing of molecular orbital diagrams of heteronuclear diatomic molecules, specifically for CO, OF, Cn-, NO+. And before we are done with this, before we finish drawing the molecular orbital diagram for these heteronuclear diatomic molecules, I'll make sure to explain everything into details. I'll try my best to do so that you'll be able to apply this. You'll be able to apply this understanding on other molecules. You can be able to apply this to draw the molecular orbital diagrams for other molecules. And at the end of this video, too, you should be able to calculate the bond order of heteronuclear diatomic molecules, right? Electron configuration, and you should be able to tell whether the molecule is diamagnetic or paramagnetic. So I will explain this to you later. So let's start. Let's draw the molecular orbital diagram for CO. First of all, let's write the electron configuration of each atoms involved in the formation of CO. So we have oxygen with atomic number of 8. Let's write the normal electron configuration of oxygen. So we are going to get S1s2, 2s2. Atomic number of 8 indicates that oxygen has 8 electrons here. So 1s2, 2s2, and then remaining 4, 2p. Sorry, it shouldn't be 4. We have 2 here, 2 here, 4 plus 4. Okay. So let's do that. Let's do same for carbon. Carbon has an atomic number of 6. So let's write it electron configuration. So we are going to get 1s2, 2s2, 4. So 2p2, giving us a total number of 6 electrons. 2, 2, 2, 6, 4, 2, 6, 7, 8. So now, for drawing of the molecular orbital diagram, we are only drawing it for the valence electron. We are going to use only the valence electron. So starting from 2s to 2p upward. So for oxygen, how many valence electrons do we have for oxygen here? So 2s2, here 2, 2p4, here 4. So giving us a total number of 6 electrons. For carbon, we have 2s2, 2p2. So 2 plus 2, giving us a total number of 4 electrons. So the sum of these, 6 plus 4, the overall electrons in the valence shell of the molecule is 6 plus 4, which is 10 electrons. So we need to calculate this before we start drawing the molecular orbital diagram. And if you are confused, I have a video for those single, diatomic molecules, A2, F2, so you can check it out to get a better understanding. So this one is the extension of that. So I don't want to make the video bulky. So this is particularly for heteronuclear diatomic molecules. So let's continue. Let's draw the molecular orbital diagram. First of all, we are going to have we have to look at the individual atoms in the molecule. Carbon and oxygen. Which one is more electronegative? The more electronegative one is going to be lower in energy. So the energy diagram is going to be tilted. So, and I will do that for you. So electronegativity increases across the periodic table from left to right. So looking at carbon and oxygen, carbon comes before oxygen. So oxygen is more electronegative as compared to carbon. So the electronegative atom will be at the right, and it's also going to be lower in energy. Let me indicate my energy flow. So let's say we have oxygen, 1s of oxygen, and then p orbital of oxygen. Then we are going to have 2s 2s orbital of carbon here, and p, 2p, 2p, 2s. I'm coming, 2s. So for this one, it doesn't change. Carbon should be here, oxygen should be here, and the molecular orbital should be in the middle. So what we are going to do is that if 2s orbital of carbon and 2s orbital of oxygen form a bond, I mean, if they overlap, we are going to get two molecular orbitals, bonding and anti-bonding. These 2s and these 2s of oxygen and these 2s of carbon overlap to give us bonding and anti-bonding molecular orbital. So we are going to have bonding sigma 2s and then anti-bonding sigma star 2x asterisk 2s, sigma asterisk 2s. So if the 2p orbital of oxygen and 2p orbital of carbon overlap, they are going to give us a certain molecular orbital. So before we draw that, let me explain this to you. We have to look at the average atomic numbers of each atoms involved in the molecule. Average atomic numbers of each molecule atoms involved in the molecule. If it is greater than or equal to 8, then this is the energy diagram that we are going to use. I mean, the sigma 2pz comes first before the pi 2ps and the pi 2py. But if it is less than 8, then the pi 2px and then pi 2py comes first before the sigma 2pz. So this is what you should know. So let's look at this. For our oxygen, the atomic number for oxygen is 8 and atomic number for carbon is 6. We are calculating for our Z average. So that means 6 plus 8. Which means the average of 6 and 8 is 7. This is 7. So 7 indicating that it is less than 8. Since it's less than 8, so this we are going to use this format for the 2p orbital. So now when the 2p orbital of oxygen and 2p orbital of carbon overlap, they are going to give us this. For this one, you can decide to separate it like this, like this, like pi 2px, pi 2py, and sigma 2pz. Or you can just write pi 2p orbitals and then sigma 2p orbital. So I prefer using this in order not to make the diagram very bulky. So I'll use pi 2p orbital and sigma 2p orbital. So if the 2p orbital of oxygen and 2p orbital of carbon overlap, this is what we are going to get. We are going to it's going to give us anti-bonding molecular orbital and bonding molecular orbital. This is the bonding molecular orbital, and the anti-bonding molecular orbital here is going to be pi asterisk 2p. And we have our sigma asterisk 2p. Like here, when the 2s orbital of oxygen and that of carbon overlap, they give us two molecular orbitals, which is the sigma 2s and the sigma asterisk 2s. The same thing will happen if the 2p orbitals also overlap. They will give us two molecular orbitals, that is bonding and anti-bonding. So let's now start filling orbitals with electrons. So you can see that for oxygen, we have 6 electrons. We have 6 electrons for oxygen. So let's do that. So for oxygen, 6 electrons. So we have 1, 2, 3, 4, 5, 6. Mind you, if you are filling this degenerate orbital, you have to fill them singly. So before you pair up. So what about carbon? Carbon has 6 electrons. So 4 electrons. So let's start filling 1, 2, 3, 4. Hope that is okay. So that is for carbon. And now, when we are done with this, we have to fold the molecular orbitals. The molecular orbitals. So we have a total number of 10 electrons. So let's start filling. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now we are done filling our orbital with electrons. The next thing we have to do is to calculate for the bond order. To calculate for the bond order. And the bond order, let's calculate for the bond order. The bond order is equal to number of bonding electrons minus non-bonding electrons, all out of 2 is the same as, all out of 2 or half of the difference. So how many bonding electrons we have here and how many non-bonding electrons we have here? So the bonding orbitals, is number of bonding electrons and anti-bonding electrons. So those orbitals with asterisk contains the anti-bonding electrons and the rest contains the bonding electrons. So we have, let's start counting. We have 2s here, 1, 2. This one is anti-bonding. This one is anti-bonding. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 electrons, 8 bonding electrons. And let's look at our anti-bonding electrons. We look for our anti-bonding electrons in the anti-bonding orbit in the anti-bonding molecular orbital. So here we only have 2, giving us 2 all out of 2, which is going to give us 6 out of 2, giving us 3. So the bond order for carbon monoxide CO is 3. So in this case, CO, the bond between CO is highly going to be C triple bond O. So that's what you mean by the bond order generally. That's what if. So now we are done with the bond order. Let's write the electron configuration for carbon monoxide. For the electron configuration, you will see that we have since when we were calculating to draw for the molecular orbital diagram, we ignore the 1s orbital. So we can indicate the one. Let's represent configuration. Represent the 1s orbital by kk, or you can decide to write it without representing it by kk. You know there's going to be sigma 1s2 and sigma asterisk 1s2. So you can write it this way, or you can also represent it by kk and then just go. So kk, then sigma 2s orbital, sigma 2s orbital. How many electrons we have there? 2. Sigma, for this one, for writing the electron configuration, we are taking only the molecular orbital into consideration. So sigma star, sigma asterisk 2s, how many electrons we have there? 2. And then pi 2p, how many electrons we have there? Pi 2p, how many electrons we have there? 1, 2, 3, 4. So 4. And lastly, sigma 2s 2p orbital, how many electrons we have there? Let me write it here. Sigma 2p, how many electrons do we have there? 2. So this is the electron configuration for carbon monoxide. Hope you are okay with this. And how do we know whether carbon monoxide is diamagnetic or paramagnetic? So this, we know it simply by looking at the molecular orbital diagram. If any of the molecular orbital is compared, then it's going to be paramagnetic. But if in the molecular orbital, if all the electrons there are paired, then we get diamagnetic. So diamagnetic means that it is weakly repelled by magnetic field, because all the electrons are paired, their magnetic moment is going to cancel each other out. So paramagnetic means electron unpaired, so attracted by magnetic field. So this one is diamagnetic because if you look at the molecular orbital diagram, all the orbitals are paired with electrons. So carbon monoxide is diamagnetic. So let's draw the molecular orbital diagram for OF. Before, let me show you something. You need to know. Sometimes you may be asked to draw dashes to join the molecular orbit. I mean the orbitals of the 2s orbitals and then that of the 2p orbitals. So this is how we are going to do it. It's very simple. In some textbooks, you will see this in the textbook. No, it's not nice, but I have to tell you this so that you. So that's what you need to also know. So molecular orbital diagram of OF, oxygen with atomic number 8. So 1s2, 2s2, 2p4. So fluorine with atomic number 9. So 1s2, 2s2, 2p5. So the valence electrons, how many valence electrons do we have for oxygen? So from starting from 2s to 2p, so 2, 4, that will give us 6 electrons. And then here we have 2 plus 5, 7 electrons. So we are going to get a total number of 13 electrons. 13 electrons. 13. I already drew the molecular diagram already. So we have to label it and then start filling. So oxygen, fluorine, and their molecular orbital will be in the middle. So for fluorine, we have 2s orbital of fluorine, 2p orbital of fluorine. Oxygen, we have 2s orbital of oxygen, 2p orbital of oxygen. When these 2s orbital overlap, they are going to give us molecular orbitals. Bonding, which is sigma 2s, and the anti-bonding, which is sigma asterisk 2s. And this one, I'm very sure that you know the reason why we have the sigma 2p orbital coming first. Let me explain. Let me go over it again. I already explained it to you. I already explained it, so let me go over it again. So the Z effective, let's calculate for the, so the Z average for oxygen and fluorine. We have atomic number 8, which is oxygen, and fluorine atomic number 9. So we add them and divide by 2. So what are we going to get? We are going to get our Z average to be 8.5. 8.5 is greater than 8. If we have our Z average to be greater than or equal to 8, then we have to use this format of the 2p orbital. So the question you want to ask yourself is that why do we have this changes in the when the 2p orbitals overlap? This is due to the effective nuclear charge. So yes, due to the effective nuclear charge. So with increasing atomic number, you see this problem comes in when we have an increase in the atomic number. So the effective nuclear charge is going to increase and then result in this. But you can do your research about it and go into details. So how many bonding electrons we have here? So 1, 2, this one contain asterisk. So those are the anti-bonding. So 1, 2, we jump this, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 minus anti-bond. Sorry, I should be including this because we are talking about bonding electrons minus anti-bonding electrons. And these contain asterisk, so they are not supposed to be included. So we have 1, 2, 3, 4, 5, 6, 7, 8. So it should be 8 minus anti-bonding. So those with asterisks. So 1, 2, 3, 4, 5. So 5. If you simplify this, you are going to get 1.5. So this is the bond order for OF. So what does this mean? This bond order. Okay, that's the bond order. General. So let's look at the configuration for OF, for the molecule OF. So we write KK to represent our core electrons. So in our sigma 2s orbital, sigma 2s, we have 2 electrons, and our sigma star 2s, we have 2 electrons, and our sigma 2p, we have 2 electrons, and our pi 2p, we have 4 electrons, and our pi outside 2p, I don't know how to write this. Pi outside 2p, how many electrons do we have there? 3. So 1, 2, 3. So we have 3 electrons there. Since we have pi abstract, so there's a need for us to indicate sigma abstract 2p. So let's say sigma abstract 2p. There's no electron there, so we just write 0 here. You can decide to ignore it. And then, is this molecule OF, is OF paramagnetic or diamagnetic? So you can see that we can tell if it is para or diamagnetic by looking at its molecular orbital. So if you have unpaired electrons, then it is para. If you have paired electrons, that means it is di. So looking at the molecular orbital, you can see that here we have unpaired electron here at pi, the antibonding orbital of 2p orbital. The antibonding molecular orbital for 2p. We have 2 electrons here and 1 electron. So the electrons are not paired here. So that means this means that OF is sorry, yes, it's paramagnetic. So it can attract a magnetic force. It can attract it by a magnetic force. So it is paramagnetic. So that is for OF molecule. So let's proceed. Same way, you can also decide to draw your dashes to join the orbitals. So you can do that. So now let's look at ionic molecules, Cn minus. So Cn minus, let's write the normal electron configuration for C. Carbon, we have 1s2, 2s2, 2p2, and then that of nitrogen with atomic number 7, we have 1s2, 2s2, and then 2p3. So what is the valence number of valence electron for carbon? So we have 4, starting from 2s to 2p, so 2 plus 2, 4 electrons. For this one, for nitrogen, we have 2 plus 3, which is 5. But the molecule has a negative charge, indicating that it has gained 1 electron. So that means we are going to wait. So 4 plus 5 is going to give us 9 electrons, right? So since the molecule has a negative charge, it has gained 1 electron. So plus 1, giving us 10 electrons, right? Good. So the next thing we need to know is our Z average. Our Z average, atomic number 6 plus 7 divided by 2, our Z average is going to be 6.5. 6.5. So this means that we just use we know how to use our 2p orbitals. I mean, we know how to draw our 2p orbitals based on this. So let's start drawing the molecular orbital. So you will see that the energy diagram is tilted. See, so the highly electronegative atom is lower in energy. Let me indicate my energy diagram. Don't forget this flow of my energy. So with this, I'm done drawing the molecular diagram. So let's start filling the electrons. Let's start filling the molecular orbitals with the electrons. For this side, the N minus and carbon, you can decide to leave it. You can also decide to fill it, so there's no harm doing it. So the main thing is that the questions that are asked, or what you need to know, is you should be able to write the electron configuration. You should be able to tell whether it is diamagnetic or paramagnetic, and then I mean, uh, and then you should be able to also tell the bond order of the molecule. So carbon here has 4 electrons. So let's for carbon. One in each valence orbitals. 2, 3, 4. And then nitrogen has 5 electrons. So 1, 2, 3, 4, 5. Done. And then we are done with this. The questions that you might be asking, that we have the gain electron is going to be effective when we are filling the molecular orbital. So we are going to fill the molecular orbitals with electrons. Then we take the total number of electrons into consideration, which is 10. So let's start filling it. Let's start filling the molecular orbital with electrons, which is 10. That total number of 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's way. So the next thing we have to do is to calculate for bond order. Bond order is called bond order equals total number of bonding electrons, half of total number of bonding electrons minus total number of anti-bonding electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 minus the only anti-bonding orbital we have here is 1 to sigma 2s, which contain 2 electrons. 1, 2. So we're going to get 6 on 2, which is 3. So the bond order for Cn is 3. So let's write the electron configuration for Cn minus, starting with the core, which is 1s. Like I told you earlier, you can decide to represent it by this. And how many electrons do we have for sigma 2s orbital? So we have our sigma 2s, which contain 2 electrons, and our sigma star 2s, which contains 2 electrons. Our pi 2p containing 4 electrons, and our sigma 2p containing 2 electrons. So that's it. So is Cn minus paramagnetic or diamagnetic? You will see that all the bonding molecular orbitals, in the molecular orbitals, we don't have unpaired electrons in any of the orbitals. So the electrons are all paired, so it is diamagnetic, meaning it is weakly repelled by a magnetic fault. So are you going to try this? Now we have NO plus. The other one was Cn minus. An ionic molecule. This one is a cationic molecule, and I know definitely we are going to lose an electron. So let's write the electron configuration, normal electron configuration for each atoms here. For nitrogen, we have 1s2, 2s2, 7 electrons, so 2p3. For oxygen, we have 1s2, 2s2, and 2p4. So the valence electrons that we have for nitrogen here, 3 by 3 plus 2, giving us 5. And for oxygen, we have 4 plus 2, giving us 4 plus 2, giving us 6 electrons. So 6 plus 5 give us 11 electrons. So since the molecule has a positive sign, indicates that it has lost 1 electron. So we deduct 1 electron from it, giving us 10 electrons. This means our total number of electrons remaining now is 10. So nitrogen has 5 electrons. So this is nitrogen. As usual, you can see that the highly electronegative atom is lower in energy. So that's why the diagram is somehow tilted. So, and it should be at the right hand side. So we have 5 in nitrogen, 5 electrons in for nitrogen. So 1, 2, 3, 4, 5, and 6 electrons for oxygen. So 1, 2, 3, 4, 5, and then 6. This is, don't forget this. There's 2p orbital for oxygen and 2p orbital for nitrogen, and then the sigma 2s, almost done. So 2s for nitrogen and 2s for oxygen. So now let's continue. I'm really exhausted. I've recorded about 7 videos, so I know you pardon me for my voice and then my actions. And don't forget to kindly support me by subscribing, liking the video, giving any comment. So that I'll be able to bring you more content like this. More contents like this. So now we are done for filling each, nitrogen and oxygen orbital. So now let's fill the molecular orbital. So we have a total number of 10 electrons, right? So let's start filling. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. So for the bond order, let's calculate for the bond order. Let me write your bond order. Now you are familiar with the formula, so let me just do this. So bond order, we are going to half of number of bonding electrons minus number of anti-bonding electrons. So number of bonding electrons, we have 1, 2. This one is an anti-bonding orbital, molecular orbital. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 minus. So the only anti-orbital, molecular orbital we have here is sigma 2s. So 2 electrons. We have 6. So at the end of the day, 6 out of 2 giving us 3. Oh, sorry. I'm really exhausted. So that means the bond order for NO plus is 3. Electron configuration. Okay, let's look at its magnetic property before. Magnetic property for NO plus, can you guess it? If we have to look for the magnetic property, we have to consider only the molecular orbital. Only the molecular orbital. So with this, there's no unpaired electrons in any of the molecular orbitals here. Any of the molecular orbitals here, how should I say it? All the molecular orbitals here are paired. So we don't have any unpaired molecular orbitals. So that means that this will tell us that NO plus is diamagnetic since all the orbitals are paired, molecular orbitals basically. So it is diamagnetic. So for the configuration, can you try this? Try this and let me see you in the comment section. So this will be your assignment. Thank you for watching, and don't forget to support me by subscribing to my channel and also liking this video. You can also share it and leave your comment in the comment section.